So hello, I'm Thomas Haines, and I'm going to be talking about a verifiable and practical lattice-based decryption mix net with external auditing. This is joint work with Xavier, Boyen and Johannes Müller. So mix nets were introduced by Chow in his paper Untraceable Electronic Mail, Return Addresses and Digital Pseudonyms, and the basic functionality is a method to turn a set of ciphertexts into a set of plaintext without revealing the link. Mixnets are used in numerous privacy-preserving technologies such as anonymous messaging, anonymous routing, and verifiable electronic voting, and hopefully it's pretty clear to you how this functionality helps in these cases, but I'll just make it explicit, at least for the case of electronic voting. So electronic voting, we often end up with the situation where there's a list of people's names next to their encrypted ballots. And we can't just go ahead and decrypt these encrypted ballots because then you would know exactly how they voted. We need to sort of mix them first, sort of analogously to the ballot box. And this is precisely what a mixnet lets us do. It lets us turn this set of encrypted ballots into a set of plain text votes without revealing who voted what, which is kind of precisely what we want. Okay, so let's sort of see how this works. So let's take the basic idea of a mixnet. We have some input, we put it into our mixnet, and we're expecting it to come out in some permuted order. So the inputs are ciphertext, the outputs are plaintext, but we expect them to be, decrypted and permuted. So inside the mixnet, there's a number of mix servers who are each mixing the ballots. So each of them is applying some kind of permutation and then doing their appropriate part of the transform. And so the input and the output should be sort of the same to some extent, have the same messages, but permuted according to a permutation, which is the product of all the different permutations used. And provided one of these permutations is unknown, it shouldn't be possible to figure out what the overall permutation is. So as I said before, mixnets break the links between the input and the output. And so this is very important in many applications, as we said in e-voting. Okay, so there are two different kinds of mixnets. There are decryption mix nets and re-encryption mix nets, and let me just give you a feel for both of these in turn. So in a decryption mix net, each mix server holds a public secret key pair, and each sender iteratively encrypts their message under the mix server's public keys in reverse order. Then each mix server uses their keys to decrypt the input ciphertext and then shuffles them. So just to make this a bit more explicit in the image, here we have our nested ciphertext. You can think of these sort of Russian nesting dolls. Each mix server strips off one layer and permutes, and so on and so forth, until eventually the plain text messages come out the other end. Okay, so in a re-encryption mix net, we're going to use a homomorphic scheme where it's possible to re-randomize the ciphertexts. So now we need a public and a secret key pair, which is shared among all of the mix servers, all of the trustees. And each sender is going to encrypt their message under the joint public key. Then each mix server in turn is going to randomize and shuffle the ciphertext. And then finally, there's going to be a collective decryption at the end. So, re-encrypt, permute, re-encrypt, permute, re-encrypt, permute, and then finally the end is going to come out. Okay. So as well as privacy, there's a need for verifiability in many applications for mixnets. So for instance, let's imagine that in this case, the inputs are bank transfers and the colors are denoting sort of the amount and the person to whom the transfer should be paid. Clearly, we don't want it to be the case that the output, does something radically different to what it was supposed to do. I'm not going to talk about this too much in this presentation, but you should also know that you can't actually have privacy for mixnets without some degree of verifiability. But it's actually slightly stronger than this. In most applications, we need something more than verifiability. We need something called accountability. We need to know who to blame if something goes wrong, which mix server misbehaved. So you need something called accountability. So as I said, verifiable mixnets are often used in electronic voting, and particularly they're used for government elections in Australia, in Switzerland, in Norway, in Estonia, and for many other elections, which are also very important. And it's therefore important to protect against extremely powerful and sophisticated adversaries. We don't want it to be in the case that in 10 years' time, somebody builds a large enough quantum computer and all of the ballots cast become public. We want to have long, ongoing privacy, and at the moment, one of the major adversaries we have to therefore consider is quantum adversaries. At the moment, there's no verifiable mixnet with external auditing in the literature that could be used for practical post-quantum security voting. Now, there's a lot of progress being made at the moment in the literature to do with practical post-quantum everything. So this is beginning to be addressed to some extent, but nevertheless, at the moment, this is true. So we provide the first solution to this open problem. So we propose a new verifiability technique called the tripwire technique, which can be used to extend any plain, that is, unverifiable proofless decryption mixnet. We formally analyze the security of the tripwire technique, and we instantiate the generic technique using practical lattice-based cryptography from conservative hardness assumptions. We've implemented this, we have some benchmarks I'll go through in a minute. If you read the paper, we give a lot more of the sort of background of this kind of technique than I'm going to do in the talk, and I encourage you to read it if you're interested. This technique is not explicitly mentioned anywhere in the literature prior to this, but it's kind of implicitly there. There's a prior work by Douglas Wikström and I believe Tal Moran where they use something quite similar. The problem is that the way they set things up, you actually can't do it practically post-quantum at the moment. So that's why this work was necessary. Okay, so at the moment, the mixnets most commonly used in practice use zero-knowledge proofs. They have basically zero-knowledge proofs that are very efficient for the fact that this thing was shuffled correctly. The problem is that these zero-knowledge proofs rely upon strong homomorphic properties of the encryption scheme which aren't there in the post-quantum versions. So the result is that there's no known proofs for post-quantum encryption schemes, proofs of correct shuffle, which are sufficiently practical for use. So that's one of the major problems here. That's starting to be addressed, but it is still hard to see how you do this efficiently. In particular, you don't really want to have to increase the parameters to the point where you could actually use some of the existing techniques. Okay, now the other thing to note is that we use a decryption mix net where most of the existing things used use a re-encryption mix net. And there's two very good reasons for this. First, if you use a decryption mix net, there's no need to do proofs of correct decryption at the end. A verifiable decryption mix net is a proof of correct shuffle. So this is a great advantage because at the moment the proofs of correct shuffle for lattice-based schemes, they're practical for some sense of the word, but when you scale them up to the sort of things we're using in an election and put them on top of everything else, it's really better not to have to do that. Okay, then there's another reason, which is you get much better privacy. Let me explain how this works. So with the re-encryption schemes, if you can change a single input, so maybe for integrity you don't care very much that you can change a single input, but for privacy, if you can change a single input, it's terrible, it's catastrophic. This goes back to some attacks by Wikström, and basically if you can change a single input, you lose basically all privacy. So if you're going to do this kind of mixnet where it's possible to change a single input, you really, really, really should be using a decryption mixnet, not a re-encryption mixnet. Okay, now let me explain the technique to you. So we start off with our basic decryption mixnet. So we have a list of inputs and we have 3 mixers and each of them is permuting and decrypting as it goes through. And in this diagram, I've marked the sort of existing inputs in blue and the tripwires in red. So the intuition is that if the mixer tries to manipulate some of the inputs, there is, in this particular example, a 50% chance they're going to try and manipulate the tripwires and then they'll be caught because we check that the tripwires, the tripwires do what the name suggests. They trigger when they're touched. Okay, now there's an obvious problem with this as I've currently presented it, which is that Mixer 1 probably knows which of these are the tripwires and which of these are legitimate messages. So we need to add something so that Mixer 1 won't know which is the tripwires and which aren't. So we're going to do a mix before our mix. I'll come back to this in a minute, but basically this gets around this first issue because now, under the assumption that one of the mixes in this first mix is honest, the mixer one doesn't know which are the tripwires and which are the legitimate messages. Okay, now there's still one more attack on this, which is that mixer 3 is seeing the plain texts of the tripwires and of the messages. And mixer 3 can therefore probably tell, which are the tripwires and which aren't. So we need to add a final encryption layer after mixer 3. And now we have the full protocol. And now I will explain to you how this works. So let me first go through the top and talk about the parties involved. So we have auditor 1, auditor 2, auditor 3, mixer 1, mixer 2, mixer 3, and then we finally have all the auditors working together for the repetition layer at the end. And we have sort of 3 main phases: the explicit mixing phase, the main mixing phase, and the repetition layer. So what happens here is we have our input messages, our blue squares, and our tripwires. And each of the mix servers, the auditors, is going to mix and decrypt, and then the mix servers are going to mix and decrypt, and we're going to get to the point just before we do the repetition layer. And at this point, we're going to check whether the existing mixing went well. So the first thing we're going to do is get all of the auditors, auditor 1, auditor 2, and auditor 3, to reveal their secret keys. So then we can just check very trivially that that mixing was done correctly. And the reason we're happy to do this is the privacy the explicit mix gave us, we really only needed while the main mix was happening. Once mixer 1 and mixer 2 and mixer 3 have committed to their mix, committed to what they've either tampered with or not tampered with, then it's fine if they know where the tripwires were. It's only that we only need the privacy for the tripwires before they actually announce their mix. Okay. And then we get the auditors who constructed the tripwires to reveal the randomness and the values used to construct the tripwires so we can check all of them correctly. So at this point, we've checked that the explicit mix was done correctly. We've checked that the main mixing, or at least all the tripwires were fine in the main mixing, which provides quite high probability guarantees that I'll come to in a minute that the main mixing was also done correctly. And now we're ready, if everything is fine, either to, well, if everything's not fine, we blame somebody. If everything is fine, then we decrypt the final layer. Now the final layer, you can either use some kind of threshold encryption scheme, or you can just have everything encrypted 3 times and they all just release their secret keys. It doesn't matter. Okay, so the basic assumption here is that the public key scheme is in CCA2 and at least one auditor is honest. Then with probability, okay, so once this is true, then the probability that more than k honest messages are undetectably manipulated is bounded by delta k, which we'll come to in a minute, and delta k converges exponentially fast to 0 as you increase k. So the more balance you want to increase, the more the exponentially smaller your chance of doing this without detection is, so the more inputs you want to change. You can also change the initial value to something arbitrarily small by increasing the number of tripwires, but this can become a little costly. So the formal theorem you can see in the paper has 6 assumptions, 2 of which I've already given to you, but there are 4 others. They're all quite minor though. And it's the concrete delta bound is as follows. I won't spend too much time on this, and if you're interested, you can read the paper. So a lattice-based instantiation. So we're using a concrete in CCA2 secure scheme, which we implemented. It's a hybrid of the lattice-based CCA2 chem with AES-based DEM with MAC. So the key encapsulation mechanism clearly closely follows the original WGEV crypto system. We implement essentially textbook WGEV. Technically it's dual, but it's okay. Which is provably secure under the now classic learning with errors hardness assumption. Implementation attempts to remain faithful to the original theoretical scheme, but rearranges it slightly to optimize the computation. Implementation targets 240 bits of security. We use 240-bit or wider data paths everywhere, including the chem-crypted symmetric session key and the DEM redundancy. Again, you can read the paper for more details if you're interested. Our test platform is a 2019 Dell XPS, i7, blah, 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 fully mitigated in microcode and OS against all known speculative execution and loading attacks. Actually, our implementation itself is not particularly vulnerable to these. We can read in the paper if you're more detailed, but more the wider system we're worried about. So here's the performance things. Basically, the high level here is basically that it's absurdly quick. In fact, we are so fast, it's not funny. But of course, as with most lattice-based things, the size of the ciphertext starts to grow, and particularly as you add more layers, it increases as well. So this is completely fine for the number of layers that we would normally see in a election scheme and in most other schemes, but it is certainly the size is always the thing that's sort of most annoying about many of these post-quantum alternatives. Okay, so just a little brief comment again on the accountability results. We've formally proven that even if all mixed servers are malicious, an adversary's risk of being caught cheating is high. And in fact, there's the concrete bound that says the adversary's chance of not getting caught is exponentially diminishing in the number of messages they change. So for applications like e-voting, where misbehaving parties face severe financial legal penalties, this is really good because they know there's a really high chance of them getting caught. Therefore, they're really going to be unwilling to do this in the first place. So at a high level, the verification procedure here is an integrity experiment that's run between the adversary and the external auditor, who challenges the adversary by injecting tripwires. So obviously the external auditor needs to be trusted for the integrity experiment, but this trust assumption is mitigated by two means. First, the auditor's role can be easily distributed among several auditors, only one of which actually needs to be trusted. This is quite a common tactic. Second, the auditor opens its complete inner state once the integrity challenge is finished, so the correctness of its internal computation can be publicly verified. So really we're trusting that one of the auditors didn't collaborate with the mixed servers during the period in which the mixnet actually runs. Okay. So as I said, we've experimentally benchmarked our scheme using our chem and our dem. It does basically what you'd expect. The key size is linear, and basically all the other operations are linear in the number of layers. It's highly practical even for large-scale elections running entirely on commodity hardware. Okay, so I said that the adversary's chance of cheating without detection is exponentially bounded, but does it actually converge to something nice, fast enough basically for us? So let's consider elections for this. Let's consider one election with 100 voters and the other with 100,000 voters. And we're going to let the number of dummies be 100,000 for both elections. So for the verifiability theorem, it follows that the risk of cheating is greater than 100% for both elections, but for different k-bounds. So in the first election, we get the k-bound for a single vote, where in the second election, you have to change 7 votes. But I guess there's an assumption here that the larger the election, the smaller the electoral margin is likely to be, so you're happy to tolerate these things. Also, we know once the result is announced what the apparent margin is, and therefore we can see, okay, if it looks close enough, then maybe, we should think about this, but if it's big enough, then we're happy. Okay. Yeah, I'll keep going. Okay, so to conclude, in this work, we've presented the first practical and verifiable lattice-based decryption mixnet with external auditing, which can be dropped into existing e-voting schemes. Our mixnet is fully implemented and supports arbitrarily many authorities. I just want to make one note, though, as we conclude here, which is there is a caveat about how we defined the goal for accountability. So our accountability goal, as I said as we went through the theorem, was that the honest sender's inputs are preserved. Now, there is a case in electronic voting that you might want not only the honest sender's inputs to be preserved, but also the dishonest sender's inputs to be preserved. Because if the dishonest sender's inputs are not preserved, then the adversary can effectively select those after the voting phase is over, sort of in the middle of the tallying phase. Now, our scheme provides reasonably good security against this kind of thing, but there's still some residual level of fairness issue here, which would be nice to remove. And with that, I conclude my talk. Thank you.